Hello guys, how you doing? Today is the first session of chapter 3 of Fluid Mechanics 1. We're gonna start with section 3.1, Newton's second law. Please accompany me till the whole video. So, as I told you, we are gonna start with Newton's second law from section 3.1 of chapter 3 of Fluid Mechanics 1. Before going on instruction, I have to introduce myself. My name is Amir Reza Talaqat and my email address is amirrezatalaqat@gmail.com. Please don't hesitate to email me and ask your questions. I try my best to give you the answer as soon as possible. So, we are going to keep on the instruction with the first principle. Guys, when a particle is moving from one position to another, it's gonna experience an acceleration or deceleration. According to the Newton's second law, we can apply the theory, the net force acting on the fluid particle under the fundamental consideration, which is Newton's second law, which means F is equal to ma. This theory states that the net force on a particle is equal to the mass of the particle multiplied by the whole acceleration that it is experiencing. But here there are important assumptions. First of all, we are going to assume this theory for a fluid that is inviscid, which means there are no shear forces on any particle of the fluid. As a result, there are no thermal conductivities, and at the end, there are no heat transfers. But in real world, there is not such a phenomena. We are having inviscid fluids, but here we are neglecting the viscosity effects. Furthermore, there are more important forces to be considered, such as pressure and as well as the gravity force. For the fluid, as I told you, as well as the gas, for the liquid and the gas, here we are having an assumption of not considering the viscous effect. But this doesn't mean that they are not important. But in here, as I told you, we are having the same assumption for both liquid and gases. Based on this equation, the net force came from the multiplication of net pressure force as well as the net gravity force, which multiplication of them is going to be equal to the particle's mass as well as the particle acceleration. But how we can coordinate, how we can describe the motion based on the Newton's second law? The answer is we have to imply it in an appropriate coordinate system, which are rectangular and cylindrical. There are more coordinate systems, but these two are more usual. The most important factor that specifies us to pick up the best coordinate system is the specific flow geometry. Here we are choosing the Cartesian model, which is in 2D plane. In chapter 6, we're going to talk about in more details of Cartesian coordinate system. But here, we just need to know the concept of the 2D plane of Cartesian system, in which the fluid particle is going to be described as the velocity vector of the particle, which is the time rate of change of the position of the particle. Guys, you should be aware of the vectors, the particle's velocity, which is comprised of quantity and magnitude. And this also means the quantity is corresponded to the speed, as well as the magnitude is corresponded to the direction. When the particle moves, it follows the particular path, which is the shape that is governed by the velocity of the particle. So when a particle is moving like this, the shape of that is going to be governed by its velocity. As the velocity changes, the shape already changes. The location of the particle along the path is the function of the particle in starting point at the initial time, and also its velocity along the path. So when we have a particle here, as it starts from the initial time, the position in here relates the distance from here. Well, for example, the position is here, the distance, and also the velocity of that. If the flow is steady one, there's no variation and changes happening in the phenomenon. As a result, all of the particles are experiencing the same action. For the inviscid flow, the shape of the flow is governed by the pressure as well as the gravity forces. But in an inviscid, let me just think about it sometime. When we are not considering the inviscid, when we are considering the viscosity effect, the shape and the path of each particular particle is not the same as the corresponding and the neighboring one. So based on this picture, we are noticing that the velocity vector is always tangent to the streamline. What's the streamline, you might be asking? The streamline is the tangent. Let me just think about it to give you the best example. As I told you, the velocity vector is always tangent to a line. You see here the blue lines. These blue lines are regarded as streamlines, which by the definitions are the lines that are tangent to the velocity vectors throughout the flow field. It's better and easy for us to describe the flow motion in the concept of streamlines in the coordinate systems. In order to grasp the particle motion in a better way, we can apply it in a convenient origin as well as the local radius in along a streamline. But the distance along the streamline itself is regarded by the particle speed, as well as the radius of the curvature. You know, when we are displacing from here to here, the distance is going to be governed by the curvature here, as well as the velocity vector. But for the particle itself, as I told you, the particle is going to be described in a velocity vector. So in here, we are thinking about the whole complex of the motion, which is going to be described in terms of force as well as the pressure. But for the particle itself, is going to be described in the velocity vector. So as I told you, we're going to apply the velocity vector for each particle. We are having the two components for velocity vector, one along the streamline, and the other one is the streamwise component, which means it is the normal one. So we're having the A as dv to dt, which is going to be round v to round s multiplied by ds over dt. ds over dt itself is the concept of the velocity. So based on this equation, the streamwise acceleration is the product of the rate of change of the speed with the distance along the streamline. This term here could either be positive, 0, or negative. So as a result, we are having the positive, 0, as well as the negative acceleration. So describing the normal component of the acceleration, we are having the centrifugal acceleration, which is expressed as v to power 2 over r. In real world, we are not having the acceleration as equal to 0, owing to the fact that round v over round s is not equal to 0, as well as we're having the curvature. So the r is varying at any instant. If the flow is already in the horizontal way, we are not having the curvature, which in further I'm going to talk about. But about the incompressible flows velocity, which are having a specific equation, we're going to talk about it in section 3.6.2. Which in there we are going to express that the velocity is inversely proportional to the streamline spacing. This means that converging the velocity vectors is going to produce a positive streamline acceleration. So by now we already know that in order to produce an acceleration, we should have a combination and the net of non-zero forces on a fluid particle, which you're seeing it here as we are converging. The normal acceleration as well as the directional acceleration, streamwise acceleration, are getting larger. Same here, as well as the same here. Guys, when we want to describe the forces exerted on a fluid particle, we have to take the free body diagram of that particle, which is out of the concept of this session. I'm going to talk about it in the following session. By now, you just have to know that we are having a weight force in this direction. The exerted force on this direction, which is along the stream. And we're going to talk about the extracting the equations out of that in the following session. Just be aware, we are neglecting the viscous forces as well as the surface tensions and any other existing not reliable tensions. So that's it, guys. We are reaching the end of this session. I hope you have got the concepts out of this video. As I already told you, please don't hesitate to ask me your questions at the comment of this video, as well as the emailing me. Looking forward to see you guys in the following sessions. I bid you all farewell.